Just 1 second. Yeah, recording. Well, thanks all for coming for our interdisciplinary seminar for the area of computational engineering and science. Our invited speaker today is Dr. Ameya Jagtap. He's currently assistant professor of applied mathematics at Brown University in the USA. He has a master and PhD engineering in aerospace engineering in India from the Indian Institute of Science. He joined then the Tata Institute of Fundamental Research as a postdoctoral research fellow, and then he moved to Brown as a postdoc in the Division of Applied Mathematics in Professor George Kanedakis' group. Well, it's the center of the STEM research around nowadays. Due to his interdisciplinary background in mechanical and aerospace engineering, applied math, and computation, his key focus of his research right now is to develop data and physics-driven scientific machine learning algorithms applicable to a wide range of problems in computational physics. He has expertise in scientific machine learning, deep learning, data and physics-driven techniques, UQ, multi-scale, multi-physics, continuum mechanics, solids, fluids, acoustics, as well as in spectra and finite element methods, domain decomposition, etc. Of course, all these fields are of our interest in our interdisciplinary area. He's also interested in the development of novel artificial neural network architecture. Please, Ameya, the floor is yours. I will ask the audience to shut down their mics. I will do it myself in the camera, and please, we'll have a 40, 50 minutes, and then we have a Q&A section. All right?
Yeah. Thank you, Alvaro, and thanks for the nice introduction. I would like to also thank Alvaro and his group for inviting me here to present my current research. And today, my topic of presentation is parallel physics-informed neural network via domain decomposition. So let's quickly see the overview here. So first, we will discuss the various physics-informed machine learning techniques that are available in the literature, brief survey, and then in particular we will discuss about the physics-informed neural network, or in short, PINs, and the recently proposed extension or the domain decomposition based PINs, namely the conservative PINs or C PINs for conservation laws, and more general extended PINs or X PINs. And finally, we will see some results, the implementation details of these two methodologies. So the traditional approaches for scientific computation have undergone remarkable progress, but they still operate under very stringent conditions or requirements. So for example, they require a precise knowledge of the underlying physical laws, boundary condition, initial conditions, and they often need time-consuming workflows such as mesh generation and the long-time simulation. So on the top of this limitation, the simulation of real observational data for ill-posed inverse problem can become very costly, where simulation need to be performed multiple times to either discover missing physics in the model or to calibrate free parameters in the model. So here is the very interesting region where we actually know some observational data. We have some observational data, and at the same time, we also know some physics. And these are actually the ill-posed problem, which due to their gappy and the noisy nature or the incomplete knowledge of the underlying physical laws, these problems are difficult to solve using the traditional methods. So here, physics-informed machine learning can play a bigger role to solve such problems. Of course, I'm not saying that it cannot solve the forward problem, but I'm saying the physics-informed machine learning can efficiently solve the inverse problem. So what is physics-informed machine learning? So it's basically a dictionary definition. So it is a process by which the prior knowledge stemming from the observational, empirical, physical, and mathematical understanding of the underlying model can be leveraged to improve the performance of the machine learning algorithm. And by incorporating the physical laws in the ML algorithms, the physics-informed machine learning seeks to build scientifically accurate predictive models. They're trying to accelerate the training of ML models with increase in data efficiency. What do you mean by data efficiency? Is by using the minimum data rather than the black box model where they use large amount of data and no physics. And also we try to increase the interpretability of the ML model to make them robust and trustworthy. So the natural question is how to make machine learning physics informed. So there are three ways. So the first one is the observational bias that amounts to training the model on data that reflect the underlying physical principle in the first place. And this required a lot of data. Next is inductive bias that amounts to designing specialized priors and architecture such that certain physical principles are encoded inclusively in the model itself. So here we need a special priors for that. And the third one is learning bias. So here that amounts to enforce the physics through penalty constraint in the loss function during model training and not directly through the architecture of the model, as in case of inductive bias. So in this talk, we are going to focus on the third way, learning bias here. Okay, so before going to an actual talk, it's a brief literature survey. So Lagares and others, they proposed neural network to solve PDEs long back in 1998. And they have several papers on that. And recently, Ohadi proposed the physics-informed neural network, physics-informed machine learning for multi-scale model for the heterogeneous multi-scale model. And Bruton and others, they proposed Cindy framework for dictionary learning of the dynamical system. Karpatne and others proposed physics-guided neural network, which is a close relative to the PIN method. Wang and others, they proposed the physics-informed machine learning technique into 2018 for turbulence modeling. And recently, Ricey and others, that's the group from Brown, they proposed spin to solve PD. And this list is incomplete. And well, in this talk, we are actually going to focus on pins. Before going to pins, let's see the mathematical setup for the neural network. This is the typical two hidden layer neural network. Here Z is my input and U is my output. Capital Phi is my activation functions, which are acting on each hidden layer. So here, weights and biases in the kth layer are denoted by WK and BK. And input Z is denoted by this expression here, the calligraphic N0, and the output at the kth layer is denoted by NK. And for the L-1 hidden layer feed-forward neural network is defined by this expression here. So this is basically a composition function here, and you can see here that's the input here, and the activation function is acting after on the output of the neural network coming from the hidden layer, each hidden layer. And in the last layer, the activation function is identity here. So that's the most general feed-forward neural network you can define. Here, theta tilde represent the set of parameters which consist of weights, biases, and this additional parameter A, which actually represents the slope of the activation function. So they are basically the adaptive activation functions. I'm not going to the details of the adaptive activation functions. You can refer this paper here. And basically, we recently proposed the general framework for the adaptive activation functions in our recent study. This is the paper, last one, sorry. And okay, the output of the neural network is generally defined like this. That's the output, and it depends on the input vector Z and the set of parameters theta tilde. So okay, so what is this physics-informed neural network? So they they actually essentially defines a paradigm for bridging the physical model and the observational data. So here we have a typical neural network whose output we are trying to match with the target data that gives a measurement loss given by this first term here. And at the same time, the output of the neural network also satisfies the governing partial differential equation or physical laws. And that gives the PD loss by this residue term here. So here, the original PD problem, we are actually converted that into an equivalent optimization problem. And our job is to minimize this loss function here. And that way, we actually can predict the solution of the given PD. Okay, so what's the advantage? So PIN can solve both forward problems as well as especially the ill-posed inverse problems. But there are some limitations for PINs. So the first one is due to high dimensional non-convex optimization problem, the accuracy of the method suffers. So here we do not get more than 10⁻⁻5 or -6 accuracy. That's the most basic problem. And the second problem is large training time. For especially for the large data as well as complex problem involving multi-scale, multi-fidelity data. So in this work, we are going to tackle this problem, large training time, by distributed machine learning framework. So basically, there are classical approaches for distributed machine learning framework. So the first one is the data parallel approach. So idea here is you have a big data. You can actually split the data into number of chunks, D1, D2, D3, and D4 into equal to the number of processors, GPU 1 to 4. And you initialize the neural network model with the same parameter on all processes. So since the neural network model is working on different chunk of the data, so the loss function will be different here. So here J1, J2, J3, and J4. And to ensure the consistent neural network model across all the processor, so a distributor optimizer is used during each epoch, which actually average out these gradients of the loss function through an all reduce operation. So to update the parameter, we need a gradient. But since different loss functions are there on different GPUs, we need to average out all the gradient. Sorry. And once it is averaged out, we are sending this gradient to all the processor in the communicator world through a broadcast operation. And finally, that way we actually get the updated parameters. And the cycle process goes on till we get convergence. So one of the shortcoming of this data parallel approach is since it's really difficult to train a large model here, large neural network model here, because of the fixed GPU memory. So to overcome that problem, a model parallel approach is proposed. So in this case, what we are doing, we have a data and we are actually dividing that data into small batches. So B1 to B4 in this case. And here, each hidden layer, in this case, L1 to L4, these are all hidden layers. They are distributed to the processors instead of the data. So here during the forward pass, once the batch 1 is processed by hidden layer L1, then the output of L1 is passed to the hidden layer L2. And then L1 will start working on B2 and so on. And once L4, the hidden layer L4 finishes B1, the backward pass kicks off. So that the backward pass means it's an optimization process where you are it's a back propagation process where you are updating all the parameters. And this way they complete all the epoch of the training in a pipeline mode. Okay. Okay. One more important point here is both model parallel and the data parallel approaches, they use a single network here, single neural network. So our approach is the domain decomposition based pins. So it's very simple. We have a domain here, and we are dividing that domain into number of subdomains and deploy pins in each subdomain. And then we stitch this subdomain through some kind of interface condition. So you can see here, we have the interface conditions here along with the PDE, and the corresponding interface loss is added in the loss function here. So now this is our loss function. Okay, what's the advantage here? Of course, it gives a parallelization capacity, but I mean, it is also true for data parallel and the model parallel approach. But then what? Then we also have the local representation capacity, because since we are using different network in each subdomain, we can actually go from shallower to deeper network as per the requirement. And then also the second thing is we can efficiently adjust all the hyperparameters in each network, in each subdomain. And finally, we have also seen a reduction of error propagation in the domain, because we are giving additional conditions inside the domain. So additional conditions, that means the interface conditions here. So we have seen that it drastically reduces the error propagation, especially during the early training process. Okay, so before going to the domain decomposition based pin, let's see the error involved in pin. So here we have U tau, which is the solution at the local minima, UG, which is the solution at the global minima, UA is the best approximation, and U exact is given by this expression here. So basically, the difference between the global solution and the local solution gives an optimization error, and the difference between exact solution and the approximated solution gives the approximation error. And the difference between UA, the best approximation, and the global solution gives the generalization error. So in particular, the optimization error depends on the loss function. And the loss function, which actually ultimately depends on the network size. And here, again, the network size depends, the approximation error depends on the network size. So they are all connected here. So once you fix the network size, the approximation, generalization, and the optimization error is fixed. But in case of domain decomposition based pins, we have separate subdomains connected through the interface condition shown by this double-headed blue arrow. And we have different network in each subdomain that gives a different approximation error, generalization error, and the optimization error. So this way, we can actually control both optimization and optimization and approximation error by deploying different network in each subdomain. Moreover, we can also use different residual points and the location of those points that actually can be used to control the generalization error. So in summary, the domain decomposition based pin can mitigate all the three errors: optimization, generalization, and the approximation errors. Okay, so this is the first example, the methodology, which is the conservative pin for conservation loss, abbreviated as CPIN. So in this case, these are the interface conditions. The first interface condition is the continuity of the flux, which is basically which we use for all the finite volume schemes. So we are actually enforcing the continuity of the normal flux along the interface. And the second is the continuity of the average solution. Here, average solution is denoted like this. When the solution is smooth, then actually this boils down to a continuity of the solution condition. It's given here. But in case of a discontinuous solution, which we can actually expect in case of a hyperbolic conservation law. So we are actually enforcing the solution, the average solution here. So it's like capturing the shock wave with a single point. So this way we are we are enforcing this average solution. We will see the advantage of enforcing the second condition, the average solution continuity condition, in the numerical section. So we can see it here. So this is a 1D Burgerish equation, simple, and that's the initial condition minus sin pi x, and the boundary conditions are 0. So we are actually decomposing this domain into 4 subdomains along x. So and they are numbered from bottom to top: 1, 2, 3, and 4. So this table gives you the all the hyperparameters used in each subdomain, and you can see the result here. So this the interesting plot. So we are actually plotting the relative L2 error with the number of iteration, and you can see here without average term the convergence is very slow, shown by the blue line. And when we use the average term, when we enforce the average continuity, then you can see that it started converging much faster. So that's the advantage of using average term. And moreover, we have also seen that for the internal subdomains where you do not have any training data, these average continuity solution, the condition can accelerate the convergence much faster. Okay, so let's move on to the next example, which is a 2D incompressible Navier-Stokes equation. It's basically a lead-driven problem, lead-driven cavity problem. So we are decomposing the XY domain into 12 subdomains. Well, here the RE is 100, Reynolds number is 100, and the left, right, and the bottoms are the wall, and the top one is the lid, which is actually moving from left to right. And this table shows all the hyperparameters which we are using. Well, I didn't mention we are using Adam optimizer here for all the cases, and for some cases Adam plus LBFGS. So here are the results for RE100. So they are perfectly matching with the results given by the GIA, which are quite standard for this test case. Okay, this is the inverse problem which I was talking about. So here, this equation is given here with some unknowns, alpha, beta, and mu, which are basically the convection coefficient, a diffusion coefficient, and a dispersion coefficient. And our aim is to identify this alpha, beta, and mu with a given viscous Berger equation. So basically my alpha is 0 here, beta is 0, and mu has some small value. So you can see that here it's the same problem what I shown earlier. So 4 subdomain problem, Burgers equation, and we initialize all these alpha, beta, and mu values in each 4 subdomains separately. And you can see that as the optimization process starts, all the values started converging to one point, and then it goes towards the actual solution. So you can see that after 1.6, 160,000 iteration, we get this results. But well, we don't have to go till this much iteration. You can see that it actually converges by around 60,000 or something. So they're perfectly matching all these values. Okay, what next? So we can actually use this domain decomposition strategy for every PD and not for necessarily the conservation laws. And also we are interesting this strategy for domain decomposition strategy in space and time. So the answer is X-pin here. So X-pin, what's the what was the interface condition? So basically the first interface condition is same as the one which we are using for C-pin, which is the average continuity condition. And the second condition is the residual continuity condition. So what we are doing here, we are just equating the residue along the interface. And that way you can cut the domain in any way in space and time. And plus additional continuity condition if you have any, say for example, the the CK continuity condition on the solution, or any other continuity. Say, for example, the if you have invariants for the equation, then you can also put. So what's the advantage? Basically, the advantage over C pin, because it has all the advantage over pin. So basically, over C pin, we can extend to any differential equation and not for just a conservation law. And it's a generalized method for space-time domain decomposition. And the interface condition, that means the residuals condition in particular, they are very simple in the sense of in terms of implementation, because we don't have to find out the normal direction as we need for in case of CPIN, where we are enforcing the normal continuity of the fluxes. So in case of a it's moving domain, or the very arbitrary shaped complex domain, it will be difficult to find out the normal direction. So that's why I said simple interface condition in terms of implementation. Okay, so this slide gives the comparison of pin, C-pin, and X-pin. Of course, C-pin and X-pin can do domain decomposition. They have parallelization capacity. They have both have local representation capacity. We can efficiently adjust all the hyperparameters. Well, in terms of applicability, X-pin can be applicable to any differential equation, not just conservation laws. The interface conditions are simple here compared to C-pin in terms of implementation. And we can also do spatio-temporal domain decomposition in case of X-pin. So let's see the results here. Our first case is again the viscous Berger, but we are decomposing the domain in space and time. You can see that this is in the shape of a dolphin. So we have two subdomains, the blue color subdomain 1, subdomain 2, and the blue C, the outside subdomain 1. So again, that's all the hyperparameters which we use for this study. And you can see that's the exact solution and the predicted solution. So the predicted solution it's seamlessly predicted. I mean, here is the L2 error here in the whole domain. This is after around 100,000 iteration. So of course, because this is not a parallel code, so when we go for a parallel, then we can see the speed up in the code. Well, the next example is the 2D compressible Euler equations. Basically, we can actually expect a discontinuous solution here. And we are dividing the domain into a peanut-shaped domain 2, and the outside domain, which is domain 1. So here, actually, this is an oblique shock reflection problem. So we have a shock at this top left corner, which actually hits the bottom wall, and then it reflects. So it actually goes through this peanut-shaped domain twice. And here are the results for X-pin. So these are the predicted value for pressure, density, velocity, X and Y direction. And this is the comparison with the exact solution. And you can see that the shock wave is captured accurately by the X-pin here, even without any. I mean, you cannot distinguish the where is the subdomain lies. So that's okay. So let's see the some high-speed performance results for the lead-driven cavity, which we have shown earlier. So this is the computation versus communication time on CPUs. So this one is for C-pin, the left figure, and the right figure is for the X-pin. So in case of X-pin, the communication time is more compared to C-pin, which is obvious because we are actually enforcing the residual continuity condition. That means we are actually enforcing the whole PD equations rather than just a flux, which has derivative less compared to the your actual PD. So you don't have to send a forward pass here. So you don't have to use automatic differentiation to calculate this interface condition, and that's why CPIN is more efficient compared to XPIN. Well, this is the computation versus communication time on GPUs. Here we use the residual points 4000 and the interface number of interface points are 200. Again, the communication time is slightly more for XPIN compared to CPIN here because of the obvious reason. And here is the weak scaling plot for CPIN and XPIN. So here we are increasing the number of subdomains and the number of resources proportionally. And each subdomain has same number of data. So you can see that both XPIN and CPIN gives the perfectly scales with the theoretical scaling. And here is the strong scaling on CPUs. Here the number of data points are same in the entire domain, and we are actually increasing the number of GPUs. And here we are computing the speed up for CPIN and XPIN given by this blue columns and the pink column or orange column. And here is the efficiency for XPIN and CPIN. So in case of CPIN, we hit almost 80% of the efficiency. But in case of XPIN, we are actually, we get around 70% of the efficiency. Okay, here is the problem I would like to discuss. That's actually the advantage of XPIN over CPIN I would like to show. So this is a steady state heat conduction problem. It's a scalar problem. And here the thermal conductivity K is a function of spatial. It's a function of X and Y, the spatial domain. And we assume that the solution is in this form for temperature T and the thermal conductivity K. And here the problem is formulated such that we know the temperature in the domain, and the job is to find out the thermal conductivity. So it's basically an inverse problem. So we are actually using a US map, and we divide that US map into 10 regions as shown here. And these are the data points. The blue cross are the data points where we know the temperature and the thermal conductivity, and we also know the temperature inside the domain. And these blue points are the residual points, and the interface points are shown by this star, black star. And in each subdomain, these are the residual points divided, and we use the adaptive activation function. So this is T stands for tan H, sine, and cosine activation functions, which we use. And here are the results. So that's the T predicted and pointwise error in T. The error in T is less even inside the domain because we know temperature values at some location inside the domain, and that's the predicted thermal conductivity, and that's the error. So you can see that the error is large inside the domain because we know thermal conductivity only on the boundaries. And that's the scaling I would like to show. So on CPUs, we almost get 10 times speed up for 64-bit precision and 9 times for 32-bit. And on GPUs, we get 9 times for 64-bit and 7 times for 32 bits. So I think that's it. So we presented the domain decomposition based pins, pin framework, namely the CPIN and XPIN, which has easy parallelization capacity and local representation capacity, and we can easily adjust all the hyperparameters. And both method can map implicitly on distributed or heterogeneous computing environment. Heterogeneous means CPU and GPU. With XPIN and CPIN, we can drastically reduce the computational cost. and it's quite a promising approach for complex problem involving high dimensional problem or multi-scale problem. And both CPIN and XPIN code are available here, so anyone can download, and if you have any problem you can contact me. Well, the future work is to use adaptive XPIN, because the natural question arises that how to choose a particular neural network architecture in a particular subdomain, because we a priori we may not know the complexity of the solution in a particular subdomain. So that's what we are doing now. So this way we can actually not only choose the network through meta learning, the network architecture, but also we can actually adaptively can choose all the points, residual points, interface points, as well as data points in each subdomain. So that's what we are going to do, working on right now. And I would like to acknowledge my contributor, Professor George Karniadakis and Dr. Khemraj Shukla, both from Brown. And if you have any questions, you can ask me.
All right, thanks a lot, Ameya. Very nice presentation. And yeah, the floor is open for questions. Please, thanks. If anybody in the audience has some question, please step in, open the mic and answer and ask Ameya.
Yeah, hello.
Hello.
Good afternoon, Professor.
Good afternoon.
Yeah, thanks for such a nice presentation. So my camera is not working. So
It's fine.
so I have actually two questions, but so the first one is that how the domain is divided in several subdomains. Is there any specific method, or it is done randomly?
Well, right now the first attempt was random. I mean, you can randomly divide the subdomains, but yeah, in the adaptive XPIN methodology, which I showed you in future work, we are dividing this subdomain as per the errors involved in the current solution. So if we have error in a particular subdomain, if we have large error in a particular subdomain, then we can divide that as a complete different subdomain and deploy the more deeper neural network.
Okay, so the domain, I mean the subdomain from which the larger error is coming, special care will be taken on that subdomain.
Yes, yes.
And second one also, you have mentioned about adaptive XPIN, but I mean till now how you have how the network is also being used on each. I mean, suppose in subdomain A you have used single layer network, and in subdomain B you have used multiple layer neural network. So how is it possible to get it know prior that on which subdomain requires more layer? I mean, single layer neural network, or on which domain requires multiple layer neural network?
Yeah, I mean, as I said, we have to do that study through a meta learning strategy, and that's the current topic of research here. So of course, a priori we do not know what should be the architecture we should use in a particular subdomain. But yeah, that's the idea here. So in adaptive.
Okay, thank you, Professor.
Answer the chat. Yes, I will share the recorded presentation later on today. Okay. Is there any other questions?
Yeah, yes, I have one.
Yes, please, Ismael, go ahead.
Thank you for your presentation, Jack. Ameya, can I call you Ameya?
Yes, please.
Cool.
Please.
Great presentation. Thank you very much. And I have couple simple questions. The first one that I've seen that you are not using any kind of regularization term in your loss training.
The only regularization term is the PD regularizer, nothing else.
Okay.
Yeah.
You don't think it's necessary to put anything else for improving the generalization of your network? Do you think it's enough?
we can use the regularization term for specifically for multi-fidelity data. We put a regularizer on the weights and biases, not biases, sorry, just weights. But whatever the problem which we have solved, we didn't need any regularizer except the PD regularizer. But yeah, of course, the it can be improved. The
Okay.
solution improved with the regularizer.
Yeah, it's a small question. Another thing, do you think that instead of using the meta learning, do you think that if you go through a kind of optimization like using Optuna or any other framework for optimizing the number of layers and the parameters in your architecture would be better than meta learning approach? Because for meta learning, you need to have lots of different examples. So
Yes,
I think it's very promising, but I'm curious about your ideas for doing this. Because in the robotics area, it's very, very common, very, very powerful. But here,
Hi, hello.
hello. Yes, I can hear.
did you hear my question?
Yes, yes, yes.
Okay.
Well, we are not hearing you well.
You are not hearing myself?
It's perfectly clear for me.
Yes, I can hear.
Okay.
Yeah, I mean, it is obvious to. I mean, of course, it is. If we go for a meta learning algorithms like a grid search, then it takes a lot of time. That because it has to do all kind of permutation and combination on each variable. And of course, then the second strategy, as you ask, it's we can go for even for a dropout, like kind of a dropout layer or something like that. I mean, you can start with a very big network, and then as the time, as per the requirement, we can shed the neurons, and in also we can also remove the layers, and that way we can actually optimize the whole network in each subdomain. Yeah, that's interesting idea.
Okay. Okay.
Can I?
Okay.
I have
Yes,
a
please
question.
go ahead, Fernando.
It's a great presentation, Maya. Thank you very much. So there is a lots of different directions you can wander, but I was thinking if you are considering applications towards real-time applications. I mean, data simulation, digital twins, things like that.
Yes, yes. So yes, we are actually working on two projects right now. One is the DNS simulation. We have the data from the DNS simulation, the turbulent data, and we are trying to infer the uh, stress strain formulation, the stress strain relation for from that data. It's a fractional relation. So that was one real application which we are solving. And second thing, we are also solving one problem of micromechanics structure, where we have data from the experimental. It's experimental data which we got from the acoustic experiment. So we have the displacement data on a plate, and the aim is to infer the material properties from the displacement data. So there also we are trying to deploy the XPin. So we have the initial results on both the problem, both the turbulence problem and the material identification problem. So yeah, I mean, we are working on the actual real time applications.
Thank you.
May I?
Yes.
Well, I mean, we have seen that the X beams, although offer more flexibility, communication time is slowed down the whole process.
Yes.
How are you thinking about to improve or at least diminish communication costs in the XPin architecture? Can you comment, please?
Well, the whole idea of XPin is to use the domain decomposition in time. So that way we can actually decrease the computational cost compared to CPIN, because you can cut in case of CPIN you can just do spatial domain decomposition, but here we can also cut it in time. So this way this can actually balance the overall computational cost compared to CPIN.
I see. Okay, I see. You are thinking about, algorithmically cutting time. But
Yes.
if you, let's say, suppose you have a code profiler, have you identified in profiling your XPin code where and why most of the communication times goes on?
Well, we have done profiling in this paper only. Well, I have not shown that plot here, but yeah, most of the communication is happening is because of the residue term. So we have to find out the in this case, in case of CPIN, you have just flux continuity. So we have one derivative less compared to incorporating the residual continuity conditions. So where we are actually incorporating the whole equation. So that's why the communication time is more in case of XPIN. But then we have also shown the example. Sorry, I don't have that example. We have shown that since we are cutting also in time direction, then we can actually compensate for the computational cost. So,
Okay.
of course, we are still figuring out how we can actually reduce this communication time through maybe some parallelization. We can actually incorporate the we can actually divide the whole interface and then apply GPU, use separate GPU for these interfaces, because in multiple direction this interface will not be a line, it will be a surface, so that will take a lot of time for communication.
Yeah, sure. Yes, right, correct. And now the framework is coded in TensorFlow, Horovod, or PyTorch?
TensorFlow.
Using Horovod.
Well, we use Horovod for only data parallelization, but then we use MPI for our position base.
Okay. So I mean, in a sense, you can, by using the MPI, you can use, let's say, something like MIDIS to provide the initial, the composition for any arbitrary domain you want.
Yes.
Good.
Correct.
Excellent.
But just one more question added to this.
Okay. Go ahead, Ismail.
When you divide your simulation through time, you are limited by the depth of your pipeline, because you reduce the number of communications between its solution, but you also are limited by the depth of your pipeline, because you have to fill in the pipeline in order to achieve the full parallelism. Yeah.
Yes.
Isn't it? Is it better? And then, because the number of communications is so heavy, that you think that going to the time division would be better?
Well, of course, if we are going in time division, then it would definitely be a better. One issue with the time division is, for example, if we have time from 0 to t, and then we are cutting from, say, into a couple of intervals. So until and unless the initial slab converges, the other slab started converging only after the initial one is converged completely. So because we have a lot of data from the initial condition, which is actually attached to the first slab, right? And then as the training procedure goes, the rest of the slab started converging. Of course, the rest of the slab, they do have data from the boundary, but not as much as from the initial conditions.
Okay.
Okay. Any other questions for Ameya?
Hi, Ameya. This is Ehsan.
Hi.
Nice talk. Thanks for the presentation, and thanks for the organizers. I have a question. I was wondering if in terms of number of domains, if you have gone to like very large number of domains with very shallow, simple networks, and the reason I'm curious is that so deeper networks, the computational time for derivatives are extremely larger than shallow networks and
Yes.
simple networks. So if
Yes.
you go to those extreme limits, almost like a finite element, for example, discretization, what
Okay.
happens and how is the training time and training number of training iterations?
Uh, well, it's a good idea when you are decomposing a domain into a smaller subdomains and then you deploy a shallower network. So obviously, you are making your solution relatively smooth in each subdomain because of the domain size. And it's a good idea to deploy the shallow network in such case so that we can actually reduce the computational cost. But in our experiment, we have done till 24 subdomain, not more than that, because we got 24. We have only 24 access to the 24 GPUs at ROM. So yeah, I would like to see more subdomains with more GPUs, and then using just deploying the shallower network. I'm pretty sure the computational cost will be very very small compared to what we are getting now.
Nice. And then the second question I had was, so still one major problem of PIN, which is a slow training time. Well, we
Yes.
can distribute it. That's one approach, but the convergence rate of optimizer is, I think, the bottleneck here. And any thoughts on improving that, or any recent works that you may have done or others may have done?
Well, yeah, yes, I agree with your point. But yeah, right now we are actually using the existing optimization algorithms like Adam and LBFGS. But yeah, we also faces the same problem because the convergence speed is still low for many large scale problem, the industrial level problem. Even with the XPin. Of course, it all depends on how many GPUs or processors you have. But yeah, I agree with your point. Yes. Of course, if someone is coming up with something very good optimizer, then hopefully we can start training in a real time.
Great. Thank you very much. Nice seeing you here.
Thank you.
Well, I mean, any other questions?
Oh,
Comments?
hi, Ameya. This is
Yeah.
Romulo.
Yes.
So I was
Yeah.
just wondering, did you
Yeah, please,
think?
Romulo, go ahead.
Oh, sorry. So I was just wondering, did you think about switching on and off some subdomains? Because, like, I like to plot the solution for pins as the epochs go on, and you can see how the problems converge. If you take, for instance, the lead-driven cavity flow, you'll see that the solution starts converging from the top wall, and the
Yes.
vortices start moving depending on the Reynolds number. So, well, I believe the same occurs with the X-pins. Like the regions in which we have more data, more boundary conditions will converge faster, and then the subdomains in the middle of the computational domain, maybe we'll have a slow convergence. So did you think
Yes.
about something like turning on or off some subdomains for some steps of the training process?
We were yeah, it's a good idea to but okay, what do you mean by turning off and on? I mean, you want to completely remove the subdomain during the training, or
Oh, not actually removing. Like, suppose that you have a subdomain close. Let's say for this problem, you have a subdomain close to the region in which you have initial conditions. So
okay,
it will converge faster than the other subdomains. So
exactly.
you could like train this subdomain for some epochs and then just freeze it and start optimizing just the other subdomains.
Okay. But
I mean,
then then the whole idea of parallel XPin is gone. I mean, if you are freezing each and every subdomain. I mean, after certain time, after certain iteration, if you are freezing the subdomain and then training other subdomains, so I don't think so we are going to get any in terms of computational requirement. It will be too much. I mean, of course, I'm not saying about the training procedure. It may result in a good or efficient training, but I'm not sure how much we can save in terms of computational cost if we switch on and off the subdomains for training.
Okay, I see it.
But you are correct that the domains which are near to the training data, they converge faster compared to the domain which are away from it. So in this case, the domain inside this dolphin region only converges when the outside domain started converging, because the data is available only on the outside domain. There is no data available for the inside domain.
Okay.
So yeah, in that sense, yes, you are correct. Yeah, but I'm not sure by switching on and off these subdomains, which will it help much in terms of computational cost or not? I'm not sure about that.
Okay, thanks.
Is there any other questions?
No, I have.
Okay, Jose Alves, please.
No, just on the wake of Romulus' question, I see I can hardly see any improvement in computational time if you switch off a part of the domain, some parts of the domain. The whole thing must go on, even in the harder parts, unless you make a new subdivision, new domain decomposition in order to forget about the domain that already subdomain that has already conversion, started all over for the remaining parts of the problem. But then it would be a new data movimentation across processor.
Dynamic repartition is always
dynamic
it's something.
Dynamic decomposition, which is
thinking about what happens in adaptive mesh refinement is more or less the same thing. You know, you have to. Yeah.
But here the point here one point is when you for example, if you remove or switch off one subdomain, you create an additional boundary for that subdomain for other subdomains, right? So if I remove this dolphin shape, then the outer the edge of this dolphin shape is a boundary for subdomain 1. So the convergence in this region will be slower, because we don't have, initially we are enforcing the residual points in the subdomain, the dolphin subdomain. If you remove these residual points, this this edge doesn't know where to go unless you enforce it from outside. So that's another issue. I'm just guessing this thing. So I have not done anything, but yeah.
Well, I mean, we are not.
I believe
communication problems with XPins in our discussion here. Right. We are just, thinking aloud. Everybody is thinking aloud here. Is having we start to brainstorm around.
I think that Romulo mentioned something like freezing conditions and boundary conditions and taking the subdomain out of the whole.
I mean, it's a good idea, but I need to.
I mean, I didn't mean that you should just turn a subdomain and don't use the GPU that was taking care of that subdomain, but like you could freeze that part of the domain and then kind of create or allocate another subdomain and use that GPU for that, like for long-time integration problems, for instance.
Yes. But that's an interesting.
There's a problem with data movement from here to there, back and forth from the.
Well, moving data around is always a bottleneck nowadays.
It's not a good thing.
It's not a good idea to change the data because
the processors try not to move them around.
Anyway, unless you use the AAMPL, the one made from people from, I don't remember the guy who did that do the task moving across the processors. I forgot the name. Don't worry.
Wow.
They say
unless you have a shared memory.
Oh, it's easy.
Yes.
Well, I mean, to me, we had start to brainstorming around more or less the same problems we face when we do adaptive mesh refinement in parallel.
Okay.
Soon, if you think about this, the subdomain and the pings is something that you have to move around, and the solution will be more or less.
Yes.
And still, there's a lot of debate and a lot of room for improvements on adaptive mesh refinement in parallel. Okay. And we are there. Of course, there's a lot of research avenues in this newer thing, but it's extended pins. Come on, it's just this is just how old is this? 6 months, 3 month old.
Yeah, it's still a developing area.
Well, it's brand new, so I mean, I believe this is a fantastic tool, and there's room for improvement. Thanks God. So we have to do research too. There's a lot of research to be done.
Yes. Any opportunities?
I'm saying this aloud, particularly for the students that are listening to me, right, Romulo, and other students that are around. There's a lot of room to make improvements.
Exactly. Yes.
They're going to run away from the room.
Yeah, the students, and now we start to run away from the room. Yeah. Okay. Well, I mean, if there's any other questions here, no. Yeah, let's thank our speaker again. Ameya, it was a fantastic talk, and very good to have you here with us this afternoon. And thanks again. And we're looking forward to strengthen our collaboration through Romulo with the group.
Yes.
And here pretty soon we'll be with you in Brown. And so things are going to be ramping up very, very soon.
Sure.
Can you share a presentation with us, Ameya?
Yes. He will share the presentation, and I will share this, and I'll let everybody knows where is the presentation and where is the recording move. By the way, can I stop recording?
Yes, you can. Very, very inspiring, Ameya. Thank you very much.
You're welcome.